Thanks a lot for having me here. It's my first time in Dortmund. And I today want to share with you work in progress. So I want to emphasize work in progress. So everything is under construction. Any comments, suggestions, discussions you want to raise, please go ahead, interrupt me at any time you want to. And what I want to share with you today is essentially just more or less like an outline how we approach a very specific question that was raised by Miriam. Sorry, that was raised by Miriam some years ago. And the tools that we want to develop in order to solve this problem. So Miriam, who's also happened to have the same family name as me, that's my wife. She's a central.
No. She was first my student, then your wife.
Sure.
Fair enough. Maybe my econometrics class.
Fair enough. So she's a central banker. She's not a econometrician or statistician, but there's a general interest from the central institutions, and not only for general understanding that the climate change and weather change has a very big impact on our life from very different directions. And those central institutions are well interested in a very particular aspect, how those climate changes and weather changes affect consumer prices. And Paolo, also a very close friend of Timate and myself, joined our team. He's a econometrician and a central banker at the same time. And so let me first start broadly with a question what we want to answer. What are the issues there and how we are thinking one should approach this problem and how one can solve it. So the question that we are trying to understand is very straightforward. We want to understand the implications of, let's say, temperature changes as one of the weather conditions or the climate conditions on the consumer price development in the euro area. Yeah. Obviously, the question is not new. It was already around for a very long time, since the so-called the Green Initiative from the European Commission. Basically, every central institution, like central banks, they're trying to approach these questions from different angles. So where we place ourselves. So from the very quick scan of the literature, which is growing and growing very, very quick, there are many more results that you can find in those that I said here on a slide. They try to sort of use the known machinery if you have in statistics or econometrics to approach this question. And as a result, they typically start working with what we call here aggregated measures. Why they do that? Because then if they work with these aggregated measures, and I'll try to be very explicit what I mean by that and why we don't want to have this potentially. It allows us to reuse all of this machinery like on VR models or local projections, what every central bank likes to use these days, perhaps dynamic panels. But it comes at an obvious price that once we start using aggregated data, it might mask some important signal for us for our analysis. And two examples of such a signals that I can present you right away is the following. At least this is the problem that we have put in front of us when we started this project. First is the sectoral aggregation. So most of the literature that I was referring to when they are talking about the impact of, let's say, temperature changes on consumer price indices, they look on inflation. Yeah, they take just some weather condition and check how overall it impacts the inflation. But of course, it might not be a very smart idea to do so. Just check whether I have it on. Because, for instance, if you decompose inflation, at least on a so I'm not an expert here, full disclosure, I'm not an economist, I'm a econometrician. So my knowledge of inflation itself is limited. But typically, you construct it as an index from several sectors. So the first layer, it decomposes on 4 different sectors like food, services, electricity, and non-services. And already looking into the zoomed components that we use to calculate inflation might be much more interesting or informative. Because, for instance, if you have a rise of the temperature summer in winter, it might have a negative impact on the prices for the electricity because we don't have to heat that much. But it of course might have a positive impact on the prices in the food sector because I don't know, the spring started too early and the quality or quantity of the crop is much worse than expected. But if you try to add those, and I'll try to show you a little illustration in a second for this argument, those effects will mitigate each other and you will not see any impact on overall inflation. Another point is, of course, a geographical aggregation. So nowadays, well, at least the classical econometrics was developing from the point that we don't have too many observations and we need to develop the asymptotics and other tools. Nowadays, we face a different problem that we have too many observations and we need to extract from this too many observations the useful information. And when it comes to the geographical aggregation, so in the literature, at least the one that we saw so far, people, let's say, take very, very generous data for some geographic region and aggregate it just into one quantity. And while we might have a really bad weather in a very important area for agriculture and good weather everywhere else, if you would aggregate this, then of course we will again mitigate the overall impact and might hide the interesting part of the information that we actually want to explore. And for this project, we have a running joke. This is how we are actually going to be on board with this project. We literally started from this paper. So the climate change will make our beer more expensive soon. And actually, it is true. So what is the intuition behind? Well, the intuition behind is very simple. And this is the map of Germany. And if you look into this paper, so it's actually a very nice way to illustrate why geographical aggregation might be very limiting for our analysis. So one of the main ingredients that enters the bean production is hops. And hops is very sensitive towards the temperature changes, meaning that it has some interval where it grows really well. But if you a little bit exceed this interval from above, then the quality and the quantity of the crop drops very, very quickly. So when we look on the map that I have over here, this is not the geographical map. Also, this is the temperature map for one particular month in June 2001 in Germany. And what would typical researchers do with this data? They would aggregate it and use only this. It will be 14.3% degrees of Celsius for the June as average temperature versus at a map where, for instance, if I'm not an expert here where the hops is grown in Germany, but imagine that the hops is actually growing in this area where the temperature in June reached 16 degrees. So 16 degrees would be the threshold where the quality of the hops actually drops quite a lot. And if this is the case, if you use this, you will not find anything. If you use this map, you will find it actually the geographical location of your information also matters. So we want to avoid geographical aggregation as well.
I think hops is grown in some area in Bavaria that runs Hallertau.
Yeah.
So it's the.
No, I didn't want to cheat with the picture, so I just generated the one that. But maybe for the next presentation,
It's like in the middle of the orange kind of thing in the lower right, somewhere there. Yeah.
Here, okay. Yeah. Okay. Now I know. Last time I presented this this slide. It was actually in Zaragoza half a year ago. There's a nice workshop for Siemens Econometrics, and they're also battling me on this slide. Because obviously in Spain they have some hops that can withstand the high temperature, but very sensitive when the temperature drops down. But at least kind of the main idea, hopefully I managed to transmit that. So the bulk of this literature that you have out there at the moment, or applied literature, they always do some form of aggregation, and the main point that we want to avoid it. So and we highlighted, so this is essentially the main outline of this project and the main goals that we are trying to achieve here. So first, we want to think, so we want to understand how can we develop some kind of a nice convenient framework that we can think about this available to reach rich data sets and try to analyze them without any aggregation. And you will see that actually the solution here is very simple. Ideologically, technically, there are of course some little problems that you'll have to overcome, and this is what I will try to talk about today. And once this methodological toolbox is developed, we can switch to something very nice, which we call the geographical index response analysis. Or if I want to be a bit more specific or technical, we can also use word functional. And of course, we want to use all of this machinery to actually answer the question from which I started this presentation and understand how the temperature changes impact the consumer price inflation. So let's start with the first one. How do we think about this problem? Well, as I said, we try to avoid aggregation if possible, and instead of looking just on inflation or on a particular sectors, we try to zoom in as much as we can. So we take basically every sector that enters in a calculation of the inflation, and I think for EU zone we have something like 89 different sectors. Later on I have slides so I can tell you the exact number, somewhere between 80 and 80 something. So we were not trying to aggregate, we will use about fixed factor. This is important for my discussion later on. And when it comes to the temperature data, I want to switch from the classical vectors to something which is called the surface or the functional variable. So full disclosure, I prepared these slides mostly for the economists, and that's why I will try to kind of step back and try to give you a little bit intuition what is the surface to functional data. There's a new, relatively new field in statistics, which is called functional data analysis, and the idea that I want to use, instead of just the point observation or the vector observations, I wanted to take the whole surface and I want to treat it as just one observation, living in some particular Hilbert space. So what I have here on this figure, I have very short time series, so it consists of 3 observations. And each observation on its own is the surface that represents the temperature over all Germany. For one particular one particular day. So I had we took the data from Copernicus. This is open source data of all of the climatic variables you can find in Europe, and they have essentially daily observations. I think they even have hourly observations from which you can reconstruct such a surfaces. And the idea that we want to kind of put in this project, how can we try to understand is there any relationship between the vector of prices and surfaces, how we can extract those. And for that, we go back to the following. We go back to the beginning. So let me put some more technical structure in my discussion. So I have 2 components. I have vector y and I have a surface x that takes the data in some Hilbert space. This Hilbert space is really well and nicely defined. This is L2, so square integrable surfaces that define over D, and D here I just use the geographic domain that I'm interested in. So on the previous example that I showed you, this would be Germany. In general, we do the analysis for the whole Euro area. And what we want to build is the following. We want to understand whether in a vector of prices, there is some directions that can be explained by some directions within our surfaces or the climate variables. And the easiest way to write down is to the so-called inner product. For my vector of prices, this will be nothing else than just a Euclidean inner product. And here, this will be the inner product that we take from O2. And you can treat it as just a projection. So what I do, I try to do the following. I take my vector of prices, I project in some direction, and try to understand whether it has any relationship with a similar object from the side of the temperature variables. And on top of that, of course, I want to put a little bit more. By the way, if there are any questions or I'm losing you, please feel free to stop me and ask the questions, because I might skip some important parts when I get caught into my thoughts. So the main idea, once again, for the beginning, how we think about this problem, I want to find two directions, one in y, one in x, such that once I project in those directions, y and x have some relationship, meaning that this coefficient is non-zero, or I can put it in different terms that the variance in those two projections is non-zero.
Systematical correlation.
This is the next slide. This is exactly where I was trying to push the method. Of course, I want to put a little bit more structure in there. So let me go back for a second. So Matteo already revealed the previous slide. The next slide, sorry. I want to do it in a structured way. So of course, what I want to do, I want to first find the first direction such that the amount of correlation between those two objects will be as high as possible. Once I found it, I can fix it, I can remove it out of my analysis, and then search for the second pair of directions such that the correlation between those two objects is as high as possible. So if I try to write down this problem, I will get the following. What I want to do, I want to solve this correlation problem. I try to project my y and x, as I said, in some directions, and try to find all of them, all of those couples across which there is non-zero correlation, and I want to do it in a structured way, in the sense that I want to first find the highest correlation, then the second highest correlation, and so on. And because of the structure of my problem, y is finite dimensional, x is not. But because of y is finite dimensional, I can have at most p correlations between those two objects, and where the p was dimension of y. I cannot have more than that by construction. And if I can do that, if I can find all of those alphas and betas, then I can write down this type of model, which will be very important for my construction of the impulse responses, or geographical impulse responses. Because then I can construct a projection operator that would extract me from x all of those directions that matters, and it will tell me which part of the crisis it does actually impact. So this is the part I did not put this terminology on. Actually, I did. Sorry. So this is what we call associated factors. So in the end, I'm trying to find sort of the factor structure on both sides of the problem. I try to find the factors for the parts of y that can be affected, and I try to find the parts of x that actually can affect y. And once I can do that, then I can form something which we call in paper associated factors.
So the different dimensionality of y is a sector that you have, or
yes, so the y is finite dimensional and have some p sectors, and x is infinite dimensional because of the surface. So how do we attack this problem? As Mate already revealed the main tool, so let's go back. This is not something new. In fact, this is one of the oldest problems in statistics. It goes back to canonical correlation analysis. This is exactly formulated the way I showed you on the previous slide. And for the finite dimensional y and x, but the earliest, actually it's not even the earliest reference that I found, but probably the most cited, this is totally in 1936. Exactly tells you how to solve this problem, how to find those directions. And in order to define and give you just without too many technical discussion around, which I will have it on the next slides, this problem is solved in a very simple way. So I need to forget about those notations for a second. Think about Cy. This is nothing else as the variance covariance matrix of y. You can think about this object as a variance covariance matrix of x and cross covariance between x and y. If I have those objects, I can define this, which is nothing else as the correlation operator or correlation matrix between x and y. And if I do a singular value decomposition of this m, this will give me this object, which is exactly what I need to find, because the transformation of this object. So if I take the singular vectors, so this is an upgraded version of principal component analysis, just for non-self-adjoint operators. So I can take those singular vectors and I scale them a little bit, and I will find my directions exactly those that I was searching for, if they exist in the first place. So this is kind of would be the main identification of what is alpha and beta in my case, how to search for those directions. Then the question, what did I do and why I'm talking so much if everything is out there? So unfortunately, there are quite a few challenges to implement this framework. So first of all, as I already mentioned, the surfaces or the temperature data, the way we want to use it, would have the covariance operator that is not invertible, because this is interdimensional objects, and we fall into the so-called famous post-inverse problem. So something that we will have to tackle along the way. There are some solutions in statistics, and I will tell you which one we try to adopt in this case in a second. But on top of the post-inverse problem, we also have a problem of time dependencies. Because what we are working with is two time series. Y is a time series and X is time series. So we need to introduce some level of dependency in our data and see when actually we can recover the correlation rate in the first place. Because the strategy to implement this procedure to find those directions is very simple. We have to just find the estimator of M and do singular value decomposition, which you can do in any software in statistics or MATLAB or whatever you choose. But of course, we have to make sure that this estimator works well if we're working with time series data, and this was the biggest theoretical challenge. And finally, when we had already the tool, we realized that it works really badly in practice. And then we discovered another problem. Even though we managed to fight impulse inverse problem, there is a problem on the fact that Y, although it's finite dimensional and its dimension is fixed to P, in a small samples, this might affect a lot our outcome of canonical correlation analysis. In fact, there are a lot of literature on that, and I will try to comment on this in a second, a couple of minutes when we get to that slide. So I think we managed to find a
Sure, the ratio should be small to lead things unreliable.
So yeah. So if P is large, or the ratio between P
is large, then the ratio is large.
Sorry.
I would think so.
I thought you all sleeping. Okay. Good. You're
Even in my sleep, you know.
Sorry, you're of course right. It has to be large. But the idea, if like in my case, in a data set that we are working with, my Y has something 80 something sectors, and the time span is 250 or something like that. So this is actually, unfortunately, very large. And canonical correlation analysis in this case is very unstable. But as I said, there is we managed to find last winter a very simple and very elegant solution in some mathematical publication. But we will get to that in a second. So let me first tell you about solution to the first problem. So yeah.
I'm just wondering if there is a problem in applied setting that is still measured on the finite temporal. I don't know, it's still not a surface, that surfaces aggregate the data.
Yeah. So
do you even need this infinite assumption of dimension?
Yes. So this very good question. So there's a point on which I'm not I'm strategically silent, because of course in practice what I have is the very dense station across, let's say, Germany, from which I reconstruct the surfaces, and then I later on I feed these surfaces into my toolbox. Fortunately, this reconstruction step has a very small error comparing to the errors that come from the toolbox. So that about that part, I'm not worried, but the question is very good, because if I would have a little bit more sparse settings, and there is a proper theoretical identification of what is sparse, what is not, this error that comes from the reconstructing surfaces can be large such that whatever I have for my toolbox, this error still will be large. In my settings, I'm not worrying about this too much. And if you want, I can tell you a little bit more about what happens on the applied part. Actually, I think I have time to comment very briefly. So Okay, so then I will tell you. This, I don't have it here on the slides because it's technically not very interesting. We use something which engineers call finite element splines that help us to kind of build those surfaces in a very, very convenient way. Let's put this one. And later on fit everything to the, treat it as an infinite dimensional object. So let me go back to the first problem. As I said, this impulse inverse problems, this is not something new in a statistical or mathematical literature. There are many solutions out there. And what we did in this project, we picked two, the most probably commonly used. This is the first one, where we use the principal component analysis to regularize what is other various exponents matrix. So what we do is we kind of decompose on a eigenvectors and eigenvalues and take first Q and hope that this would kind of give us the full information about the variance matrix and allow this number of eigencomponents that we choose to grow with the sample size when it comes to the asymptotics. And the other one, this is equal or probably rich regularization a bit more known. We add something little to the variance matrix such that we can invert it and then play around with this tuning parameter in the limit to see where we can recover consistency. So the first method was proposed by, in a similar settings by He et al. And then with the Tikhonov regularization in slightly more general settings, not general, different settings, was considered by Elvan Singh, and actually they have a very nice book written for the whole topic, how to do that properly. This is, we can skip this. This is just a technical presentation. Let me just comment very quickly. We can show the existence of our variance operator. Remember, this one is not invertible. I need to make sure that overall object can exist. And we choose a very simple solution here. We just make sure that the range of those operators are properly defined. And if this is the case, this is the condition from He et al. Or equivalent that allows me to make sure that my correction operator is properly defined. And if it's properly defined, then I can do single validity composition. If we can do single validity composition, then I have my directions for which I was searching. Just to assure me that there is a theory behind that we can identify properly our correlation operator. As I told you just a couple of slides ago, if you still can listen to me, to my monotone voice, the biggest problem for us was the fact that we need to introduce a time dependency sort of, and allow for different settings depending on what we want to obtain. And it turns out to be not as straightforward as we want. So the first approach that we use here is to allow for something which is called lemma approximability, or maybe you're more familiar with the term Bernoulli shifts. This is a very old way to define time dependencies between, time dependencies within one process. It goes back to Billingsley group for classical time series analysis and was relatively recently proposed in Annals of Statistics by Herman and Kokoschka. Those settings were brought to the functional data analysis form if you want the surfaces. Another approach that we, I will try to comment why approach one might be a bit too restrictive for our case. And the second approach to introduce the time dependencies in our theory was to use something which we call the moment-based notions. So there is one version of it in Galevitis, his famous geographical metrics 2003. And it's something that I try to extend this framework with Alex, another student from Bond, to functional data. And the idea of this moment-based notion, I don't have it on a slide because I don't want to lose you already in so many notations. The idea is very simple. So this moment-based notion allows me to control for the speed of decay of autocorrelations and to control everything about the second moments I use the equivalent condition. So something that this is kind of machinery very similar for commonly used in a classical time series analysis. The beauty of that, again, we don't have to stick to the strong stationarity, the strict stationarity that we have in the first approach. We only need a stationarity up to the second moment. And this approach also allows us to potentially, if we want to introduce something which is called low-run dependence in our data as well. So both approaches, it doesn't matter which one we choose, comes with a lot of additional machinery behind it we have to introduce and impose so we can solve the problem and make sure that our estimator actually estimates what it has to estimate. And then we choose two paths here. So one, we use the PCA regularization with the L4M approximability, and the second one, we choose the Tikhonov regularization together with moment-based dependence. A quick summary of both approaches. They work well. We can prove adding some additional restrictions. So how people, I should talk about it. So I will not torture you too much. So when it comes to the principal component regularization, there's always a problem how many principal components we have to choose. And in the statistic literature, this is tied to the very often to the spectrum properties. So how close are eigenvalues to each other? The multiplicity of those eigenvalues have to be 1, so they should not repeat each other. And there are a lot of assumptions are imposed in those settings that cannot be verified in practice. So in order to make everything work, we use a trick from the node done by Horman and Kaczynski that allows us to sort of select number of principal components in a data-driven manner, but it also has some hidden implicitly assumptions on a spectrum that we cannot avoid. What's good about this approach that it's super easy to implement. Essentially, we have to do some principal component analysis of the variance covariance matrix first, and then you can construct the estimator of the cross correlation. But the problem is that, again, it requires some unrealistic restriction on the eigenvalue spacing. So if you believe in that, that's fine. Then we can prove that we can derive here a consistent estimator of the correlation operator. But what was bothering me more is the strict stationarity. So otherwise, this method will not work. That's why we also consider another possibility to use the Tikhonov regularization with moment-based notions. There, we have even weirder regularity conditions that we have to impose. Comes from the very long-standing literature developed by Marie Carrasco and Jean-Pierre Florence. They have a very just a reference. They have a very nice chapter on the imposed problems, a very general mathematical approach. So both of them are mathematicians, and they find a very nice way to work with the imposed inverse problem. Sorry. The price for that, we have to impose some regularity conditions that's a little bit hard to explain on the go, but the main idea that this type of assumptions through the parameter beta, I can control the degree to which the problem is regularized or not. And by pulling my parameter, I can kind of have a better feeling what's happening with my problem. So if I'm willing to pay the price of this different regularity conditions on my problem, then I can show that the Tikhonov estimator, so here parameter alpha simply stands for the little something that I add to the variance covariance estimator, so I can invert it, so I can also control that. I can prove this result, and this is here there are two terms. It's highlighted in red because I still have to verify those rates, but the main idea is very standard. This is variance bias trade-off. One is responsible for variance, one is responsible for bias, and depending on how I play around with alpha and beta, then I get the result that I want. Any questions to the a little bit more technical part? I promise that there will be no more technical slides. Okay, so let me tell you a few words about the last problem. This we notice when we actually try to apply our toolbox to the real data, is that even if you can fight the fact that Cx of a variance covariance matrix of X is not invertible, we still run into the problem that the final objects that which we are working do not produce the true canonical correlates, canonical variables, sorry. And to illustrate to the issue, let me show you a very simple example. Monte Carlo experiment. Imagine that I take two vectors, x and y. Forget about everything what I told you. This is the fixed vectors of length 30. I generate them independently of each other. I do this 1,000 times. So I obtain a sample that has 1,000 components in there. And I try to calculate whether there's any correlation between those two objects. But remember that the key point here, I generate them completely independent of each other. But what I will find that actually there is quite some level of correlation between those two vectors. So, and the highest correlation will be something like close to 0.3. And it turns out there is the whole literature behind that explains you why this happens and why did we find sort of like a non-true correlation between two objects. And it's mostly related to the fact that the dimension of my vector space is relatively large when I compare it to the overall sample that I have. And it took us a very long time to understand what's happening. And actually the solution we found in a very old math paper that explains what's happening. And back there in 1980, actually proved that in a small finite samples, we derived the distribution of the fake correlations and the threshold that I have here highlighted. So what this result tells me that if I calculate or if I find any correlations between two vectors, and these correlations are below this threshold, we cannot distinguish them from the noise. And if I find something above this threshold, this will tell me that this is a really true correlation. And then there are some additional tools that will tell me how to correct in order to remove the bias. And the idea of the method is very, very simple. The only thing what I have to do, I need to do my canonical correlation analysis. I need to calculate the threshold and check how many correlations I have above. And this will be the solution that we use for the last part. Or for the case where dimension of x, or well, in my case, dimension of y is not too small. So a natural part to or missing part that I'm not going to present today is some basic Monte Carlo simulations to tell you how this method works in control settings. This is something that we are working on and trying to understand which of the estimation methods that I told you about is actually working that in a small settings. But once we have this methodological toolbox, once we know how to extract those directions, how to extract the associated factors, we actually can construct and use it for something much more intuitive and I would say nicer or easier to sell. And this is what we call geographic impulse response analysis. So for that, let me introduce some additional notation. So y, as before, this is the vector for prices, and I want to understand which part of the prices can be affected by the temperatures. And when it comes to the impulse response analysis, of course, macroeconomists want to make sure that I control for everything that is relevant for the analysis. So I can include also lags of my temperature maps. I can include the lags of my prices. I can include another surfaces that control for the precipitation or sun radiation or some other macroeconomic variables that comes to your mind. So my new x will be actually, I will denote VT, and this VT will just contain a little bit more information than before. But once I have it, what I can do, I can use this toolbox to construct this type of object. If you can remotely remember where I started this application, this presentation, the pi was the operator that I wanted to sort of identify and estimate. And this pi is exactly the one that I obtained from the canonical correlation analysis. It tells me which part of VT helps me to explain some parts of y t tilde. And y t tilde is already kind of notation tells me only the part of y that is affected. I can, if I properly define the space where my VT lives, I can rewrite this model in such a manner where the first component, if you're familiar with local projections, this is sort of how Oscar Horda sells it, a way to estimate impulse response analysis without knowing the true data generated process. But if you look very carefully on what is the first component in this sum, this will be exactly the kind of the generalized version of the local projections that Horda has. Just in my case, it will be designed for surfaces, not typical vectors as we have it in the original paper. And we can use those. So I will switch to sort of like a pseudo application because we didn't finish that, but I only will want to give you a very brief idea of what we expect to obtain in the end of this very long and demanding project. So our original setting is the following. We have YT that has 80 sectors. So I was wrong about 89. We also have a data that starts from January 2001 up to 2021. Our climate variables we take from this Copernicus data set, and it's very, very dense. So we have essentially the grid, I think it was 25 kilometers apart from each other. We can even take it more granular, I think 10 kilometers, but there's very little difference in between, and my laptop cannot handle that. So we also have the historic temperature data. So we actually use data from 50s to 80s, what we call the historical background, and we want to understand how much it deviates from the last 20 years. This is something, by the way, there was the question how I reconstruct the surfaces. I was very silent on that because it's a rather boring and very long procedure behind, but also very well understood by engineers. They use something that is called finite element method. To reconstruct the surfaces, there's very many nice tricks behind this method, and it allows us to analyze many nice properties of the surfaces, but I'm only interested in reconstructing my data from the grid. So the first, what we obtained, this is again, this is not about our method, but something that was rather stressful for me to see. So this is the historical mean surface for Europe area from 50s to 80s. What I did, I sort of uploaded the average surface for 30 years, and well, you know, the Spain is, or the south is hotter than the north. There's nothing surprising here. What was stressful for me is the second part of this plot, because this is deviation from this historical mean in the last 20 years. And there's, if you look in this climate discussion, there's a goal not to exceed 1.5 degrees of Celsius. And if you look carefully on this map, there are many areas in Europe where we already increased the average temperature more than by 2.5 degrees of Celsius. So what we want to, again, this is not a final pictures. This is just what do you expect to have in the end. If I program my method correctly, which is not, and this is supposed to be impulse responses method. I will explain myself in a second. Here, that's look very bad. What I want to do, I want to have a method that allows me to shock a particular geographic area and see what will happen with the rest of the prices. So what I have here, I shock the whole Europe. This is very horrible picture. I shock the whole Euro area. I know.
How many digits do you have to
Let's go to this. This one is better. So what I did here, I shot only the upper part of Europe by 1.5 degrees. And I see what happens, well, at least I want to see what will happen with every sector that I'm including into my analysis. When I have this spaghetti plot, again, this is wrong. This is just to give you an idea. We found a mistake in the code, as always. And here I color coded all of my sectors. So the blue one stands for the food, the green one for the energy, and the purple one for the rest. This is services and non-services. And yeah, so this is what we want to have in the end, where we try to sort of run the analysis. We try to show different parts of Europe and see what will happen with my impulse response analysis. I don't have, unfortunately, a result for the beer. Actually, I do have, but I don't have it here. So that if I shot the whole Europe by 1.5 degrees for 1 month, the prices will rise and the effect will last more than 6 months. So the effect is actually quite big, but I don't have it, unfortunately, on the slides. Yeah. Maybe I will change that. So that's more or less everything what I wanted to tell you. As I told you, this is still everything under construction. There's still many angles that we have to think about, tailor, improve, and hopefully soon you will see a proper spaghetti plot of the paper.